Hello students, so let's go for a revision of next topic of quantum mechanics. Today I will just discuss you where we should focus mainly on free particle and step potential. These two are very important topic, and every year at least one question will come from this particular section. So if I am talking about free particle, that means I am talking about the constant momentum. So if you have Hamiltonian, then your Hamiltonian for free particle is basically px square upon 2m. So I am just talking about a kinetic energy. There is not any potential energy, and sometime you can have constant potential. So that is not big issue. So what is wave function? The wave function is basically a e to the power ikx, and the another wave function can be possible e to the power minus ikx. This wave function have momentum h cut k. This wave function have momentum minus h cut k, but these two have same value of energy, that is h cut square k square upon 2m. So same value of energy have two different eigenfunction. That means they are doubly degenerate. Doubly degenerate. So you should always keep in mind that basically this is energy eigenstate for momentum as well as energy. This is also energy eigenstate for momentum and energy. It has momentum minus h cut k, but it has momentum plus h cut k, but same value of energy. The next concept you have to just go for the probability current density. So if you are going to calculate probability current density, and this thing can be easily calculated by h cut upon 2im, and this value is equal to psi star del psi upon del x minus psi del psi star upon del x. So this is your probability current density. So you can have a probability current density. If you are in the classical region, then you have some positive probability current density, and that value is equal to this jx is equal to rho into v, and which can be written as mod psi square and momentum by mass. So you should remember this formula for the current density, and this is in the classical allowed region. So this is in the classical allowed region. And in the classical forbidden region, we have current density, which is 0. So this is in classical forbidden region. But you have to always keep in mind, there is probability density into classical forbidden region. So in the classical forbidden region, we have current density which is 0, but there is probability density. This is very important concept, and you should also figure it out. Suppose there is a superposition of wave, something like a e to the power ikx plus b e to the power minus ikx, then, and if the particle has mass m, then the associate current density is equal to mod a square minus mod b square, and this will be h cut k upon m. So you should always keep in mind because this current density is associated with the momentum of a particle. So this will just tell you incoming momentum, and this will just tell you outgoing momentum. So complete momentum can be written in this thing in this way. So you should remember this formula also. And the concept of current density will also go for the basically a step potential. So you have this concept of a step potential. This is V naught. This point is 0, and this is greater than, this x is positive, this is negative. So we can write we have two condition. When first condition is E is greater than V naught. If E is greater than V naught, you can have psi 1 as a e to the power ik1x plus b e to the power minus ik1x, and psi2 is equal to c e to the power I k2x. And you should also remember what is value of k1. The value of k1 is equal to root under 2me upon h cut square, and value of k2 is equal to root under 2me minus v naught upon h cut square. So you should always keep in mind how your wave function is going to travel into this particular thing. And you can also remember the one very important formula, that is reflection coefficient as well as transmission coefficient, and what is relationship between reflection and transmission coefficient. So we can use this particular thing. So the reflection coefficient here, if E is greater than V naught, you can find this is root under E, this is root under E minus V naught upon root under E plus root under E minus V naught whole square. Once you can calculate the reflection coefficient, you can easily calculate the transmission coefficient, that is 1 minus reflection coefficient. So this is very useful formula for this step potential when E is greater than V naught. So you have finite reflection. Even if energy is greater than V naught, the particle can reflect back. We have discussed all this thing into our quantum mechanics class, but you have to focus mainly on this part. And you have to also learn how to plot the wave function into two region, mainly that probability density into two region. So if energy is greater than V naught, so you have, suppose this is my potential. So if energy is greater than V naught, then this is my probability density in this region, and here we have constant probability density, because you have only this wave function, and this will be sine function. So you should always remember this thing. And the second case is when E is less than V naught, then you have this particular condition. The energy of a particle is something like this. Then here you have psi1 is equal to A e to the power I k1x plus B e to the power minus I k1x, and psi2 is equal to, let's say, C e to the power minus gamma x. So again, the value of k1, this is my region 1, this is my region 2. The value of k1 is again root under 2me upon h cut square, but the value of gamma, you should always remember, that is 2m v naught minus E upon h cut square. And if you are going to draw the probability density, then this will be, in this region you have sinusoidal wave function, but here this is decaying in the nature. So this will be e to the power minus 2 gamma x type of function is here. So you have to always remember this thing. And here the transmission coefficient you will get 1, and reflection coefficient you will get, sorry, in this case you will get the transmission coefficient you will get 0, and reflection coefficient you will get 1, because in this region there is not any transmission. So this thing you have to always remember. But in this, even if transmission coefficient is 0, there is probability density, and this is your probability density for this step potential. So this concept is very important. You should work out in which region which type of wave function is there, how you can plot it, what will happen to the wavelength, what will happen to the amplitude. This thing is very important. So why working on this particular thing, you should always remember that your wavelength, sorry, your probability density is proportional to 1 upon momentum. You should always use this particular concept. Whenever your momentum is decreasing, your chance to getting the particle at that region is going to increase. So here this concept is also very important. So just focus on all this part, do the previous year question based on this thing, and you can just you will see that more or less question are coming only into this particular concept. Yes, the reflection coefficient, transmission coefficient for E is greater than V naught is very important. And for E is less than V naught, you should remember the transmission coefficient is 0 and there is 100% reflection coefficient. And yes, what is the actually probability density? So I am just plotting this thing as a probability density. This is also probability density versus X. So this is all about your main focus of the free particle chapter. Thank you.